your thoughts on this work today. So I'm going to talk about sort of a body of work that I've been playing around with for the last few years, really sort of 3 or 4 years, trying to employ dispersion relations that are understood in quantum field theories for understanding the structure of the effects of physics beyond the standard model, and with the hope of sort of generalizing. And sort of generalizing, you know, in the context of effective field theories, but also in scenarios where effective field theories cannot be employed because the new physics is light enough to enter processes on shell, meaning that there's no such thing, there's no effective field theory approach, there's no scale separation. Nonetheless, quantum field theory has a few tools tricks up its sleeve, which lets us to say a few things that are very general, even when new fields are not decoupled, when we're not working within an effective field theory. So this talk will be sort of split across these two topics, with the odd little bit of historical analogy here and there. I would very much like, if you want to ask a question, I think normally we raise our hand within the Zoom call and wait to be asked, but to be honest, I would prefer if you just speak up and interrupt me in the way you normally would in a seminar, because I would very much appreciate any interaction during the talk as well as afterwards. Okay, so let me check the time. So the first part of the work is really concerned with a question that I think is quite important, and it's a question that we can discuss with our colleagues in other fields and even with lay people who are just interested in science. And the question is, how does the Higgs move? We spend a lot of time discussing things like, what are the Higgs couplings? What is the Higgs width, which is sort of related to how it moves, how it decays. What is this Higgs self-interaction? We connect that often to the question of what is the shape of the Higgs potential. But I think equally important is the question, how does the Higgs move? How does the Higgs field, under some assumptions of course, but how does the Higgs field get from A to B? In other words, what is the Higgs propagator? Now I find this to be a very, very important question, and I think it's one that we should as a field strive to be able to answer. And as you will see in the next 20 or 30 slides, this question is actually one that's extremely difficult to answer. Right now, we have no idea how the Higgs moves. We have essentially no constraints on BSM corrections to the Higgs propagator. Although in future we could access them, but the story is actually unsurprisingly very similar to the story for the Higgs self-coupling, in the sense that any answers we can get at the LHC are really quite unsatisfactory, even at high Lumi, and that ideally one would go to a much higher precision machine or higher energy machine or higher precision machine to try and dig out these effects. Okay, so yes, so essentially, the question is, how does the Higgs get from A to B? And we don't really know this at short distances. Of course, if the distance between A and B is very long, then we do know. But if the distance from A to B is much shorter than the wavelength of the Higgs, the quantum wavelength of the Higgs, then we actually really don't know. It's an unanswered question at the moment. However, we can hope to answer this question by sort of structurally identifying what we even mean by the Higgs propagator, by structurally identifying what it is in the standard model and what it could be beyond the standard model. And to do this, it's useful to go right back to the early days of QFT, the days before even renormalization was properly understood in quantum field theories, and look at the sort of tools that people had before they really knew how to do perturbation theory in general quantum field theories. And what's interesting is that in those early days of quantum field theory, some very smart folks did, put a lot of effort into deriving and identifying quantities that were, not really observables in every case, but quantities that could be calculated within quantum field theory without relying on perturbation theory, so non-perturbative quantities. And my favorite is the Kallen-Lehman representation, but there's others, of course, like scattering amplitudes, the analytic structure of scattering amplitudes, things like this. Kallen-Lehmann representation, I think it's meant to be pronounced Challen, but I'm not sure. But this is essentially a statement about the 2-point function, the propagator of any scalar gauge neutral operator. So if you have any scalar gauge neutral operator and you want to understand this guy here, this quantity here, you can understand that in the full Hamiltonian, the full quantum mechanical theory, there will be a complete set of momentum eigenstates, and they're complete in the sense that they are, well, they're eigenstates in the sense that the momentum operator on that state gives you just the momentum of that state, and that times the state, and that also they're complete in the sense that if you sum over all of these states and integrate over all of their possible momentum, you have to get an operator which is equivalent to 1, to unity. So we can take this operator and just literally sandwich it in between the two insertions of the whatever this scalar operator is. And this doesn't have to be, you know, a single field like the Higgs. And this could be like, you know, 17 Higgses or something, or, you know, 4 fermions or whatever, this operator. It's just any scalar operator can be composite. So you sandwich these states in between and then use momentum, the fact that these are momentum eigenstates, and act with the momentum operator to write this in this form. So we've done nothing to it, we've just put 1 in, essentially. And you can see in this form here that we get the modulus squared of a matrix element that you're integrating over and summing over all of the momentum eigenstates of the Hamiltonian. So this guy here is a positive definite quantity. And so then we can take this and insert 1 again. So what I've done here is I put a delta function between px and p, and then integrate over all p to just recover this initial guy here. So we've sort of put in 1 again. And then you see that this 2-point function is the Fourier transform of this object here, which is entirely positive definite. And also, because the Hamiltonian is bounded, it has some lowest energy eigenstate. Otherwise, it would be you wouldn't have a stable vacuum. You can write this term here in terms of this term here as being 0 until p becomes positive. P0 is positive, so the energy is positive, multiplied by some positive function of p squared. We've also used Lorentz invariance here because this can only be a function of a Lorentz invariant quantity. And so we put this in here and we can just relabel these things. So we can rewrite this integral here as an integral over all q squared of something which is fundamentally a function of just x and y here. And then finally, we want the time-ordered 2-point function, a time-ordered propagator. So we just take this thing that we just calculated and then add, we didn't really calculate, I didn't calculate anything here. This has just been a massaging the same function from the start, and then add the same function with the times swapped with a theta function, just so that if they're in the opposite order, then the time-ordered correlation function has y and x swapped. Recalling that this function here, which is defined as this guy is equal to this guy, is essentially, when you add it with the Heaviside theta function to do this time-ordered version, it's actually the Feynman propagator. This is the definition of the Feynman propagator. And so finally, this tells us that the time-ordered 2-point function is this Fourier transform of a function just of p squared, where this function of p squared is the integral over some positive definite function multiplied by the Feynman propagator. And this is the Källén-Lehmann representation. And as you'll have seen through these steps, all that's really been imposed was unitarity. That was when we inserted 1. Causality, which is when we did the time-ordered thing and wrote it in terms of the Feynman propagator. And relativity, where we assumed that a function of the 4 momenta is a scalar quantity, so it had to be a function just of p squared. And those were all of the assumptions that went into it. But this is very powerful. This applies to any scalar operator. So this, you could deploy this in many different places. A similar logic was used, for example, in the sum rules, doing for deep and elastic scattering and things like this, using current algebra. A lot of them heavily relied on essentially the vector version of this. But we can use it in BSM physics in a number of places. So for instance, if we consider the Higgs 2-point function, I've just done a translation to set x. translated x to the point 0, which I can always do just by translating my entire coordinate basis. I can write the time-ordered Higgs two-point function must also have a Källén-Lehmann representation. And we know what this is. For example, if the Higgs were just a free field with no interactions at all, then this rho quantity here, which is essentially the density of states, tells you that there is only one state that you can create out of the vacuum, which is the Higgs at its mass, at its energy. So this rho function becomes just a delta function. Put this delta function here, you get just 1 over p squared minus m squared. So you just recover the Feynman propagator that we all know and love. And we've even measured the position of this pole, right? It's 125 GeV. In the standard model, it's not so simple, because in the standard model, you have the pole, which is where the Higgs is, but you also have all these other multi-particle states. The Higgs operator can create from the vacuum a Higgs, but it can also create, you know, a pair of electrons, a pair of W bosons, and things like this. But at least the right-hand side is calculable within the standard model, and it's always positive because that quantity was positive. But what if there are states beyond the standard model? I mean, we know there must be states beyond the standard model, but what if there are states beyond the standard model that aren't too heavy, aren't too far away from the electroweak scale? Then this density of states function becomes the density of states in the standard model plus some density of states that involves fields beyond the standard model. It could just have fields beyond the standard model, or it could have some mix of multi-particle states that involves standard model states and BSM ones. But we know that we recover the standard model limit when this guy goes to 0. And of course, rho of H is always positive. And rho of standard model is always positive because there is a limit in which if all heavy states, BSM states, were decoupled, this would still be a fully sensible quantum field theory. So this is positive too. Okay, so returning now just to the momentum space propagator. So we're just doing the Fourier transform of the position space one. It looks like this. And we see this density of states is associated with the poles and branch cuts at the mass scale of any new states, or any states in the standard model for that matter. What this means is that if the BSM states are heavy, if all of them have mass above some threshold, let's call it big M, then rho of X is 0 up until that threshold. So from this statement alone, the fact that it's positive and the fact that it's 0 up until the mass scale of the new states allows us to make some completely general statements, which I think are very powerful. The first is that if we expand the propagator in small momentum, we can just do this integral and always work at p squared below m squared. Then we can actually tailor, if p squared is always below m squared, then this guy here is always smaller than this guy here. So we can actually just Taylor expand this entire function and do the integral for each term in the Taylor expansion. And the answer we will get is something like this, which is not surprising. It says that the two-point function of the Higgs operator as the standard model piece, plus some Taylor series in p squared over m squared, where m is the mass of the new states. This is completely in line with our expectations based on effective field theories. But this quantity Cn here is written in terms of, I've just done a redefinition of variables to write it in a slick way, where now x is a variable that goes between 0 and 1, and it's related to the p squared going between m squared and infinity. And this is the density of states here, where the change of variables has dragged x into this place here. So you can see the dependence on the initial, q squared in that integral. And we see that they're related. Now this is a function of x, and this is a function of x between 0 and 1. Higher powers of x are smaller, because this is always between 0 and 1. So if it's x to the 10, then that is always smaller than x to the 7 or x to the 3 or something like that. So straight off the bat, we can make some very general comments. The first is that all of the Cn's are positive, because this quantity here is positive, so the integral is positive. So any BSM corrections to the Higgs propagator in an effective field theory will be positive. The second is that because of the way we've written this integral, you can see that Cn plus 1 is always smaller than Cn, because it's the same integral integrand here, multiplying a function of x, which is always smaller for larger n. So we see that not only are these coefficients positive, but they actually must form a convergent series. The Cn is always bigger than Cn plus 1. Furthermore, that means if C10 is non-zero, then C8 has to be non-zero. You can't have corrections that just turn on at some very high power of the momentum, 18 powers of the momentum or something like this, the form momentum. That's inconsistent with quantum field theory, which is not something that's automatically obvious, I think, from just playing around with toy models. Yep.
Matthew?
Yep.
Just one quick question. So don't you want an additional constraint that the ratio Cn plus 1 upon Cn goes faster than 1 upon 1 upon n to for it to be convergent, or is this enough?
So this is enough. So by
because
fiat,
there's a power here. Okay, fine.
yeah, we're working at p squared below m squared by assumption.
Okay. Yeah, I forgot this. Okay.
So yes, so we called it convergent, but of course, these CNs don't know about p squared over m squared. So this is a statement independent of that, but it implies that this series indeed, as you are suggesting, them, this in some sense implies that the actual perturbative series itself must be convergent, because p squared is always less than m squared. And it's convergent. It only starts to violate convergence if p squared is really at m squared, and if the theory is such that all of these CNs are equal. And that's in fact what happens when you have tree level contributions. If you have the Higgs has like a tree level kinetic mixing with some other heavy Higgs, you saturate this bound. It's actually all of the CNs are 1. Thank you. That's a great question. Any other comments?
Yeah, Matthew, I have a live question.
Yep.
So can you go back to the last slide?
Yep.
So there is so the way you have formulated, right? It feels like that EFT sort
Yes.
of emerges.
Yes.
The worry is the violation of decoupling, right? So I mean, if you think in terms of like in standard model, right? The violation of decoupling comes when you consider. I mean, what I mean by violation is that you take m to infinity, yet you get finite pieces, right? So this comes from like if I include for new physics coupling lambda, let's say, I'm just trying to draw an analogy with the top cases and how it violates the decoupling theorem, right? So in the top cases, when you decouple top, you still get effects which are only suppressed by V, right? Electroweak wave. It doesn't decouple with top, right? The so in an analogous situation, imagine that your Higgs coming from a coset, right? In those cases, decoupling theorem might break down. So in what I can imagine that when it's not just a function of m squared by x, it could be, for example, some function of m squared by, let's say, lambda squared by x, where m over lambda some finite piece, finite, just like, m top by y top is v, which is held fixed, right? So if there's like a 1 TeV, 1 TeV baking down to, electroweak theory, right? You could still have some effect which is going as 1 over v to the power n, not as 1 over m to the power n, right? Wouldn't that some way get reflected over here? I mean, what I mean by that, the new physics parameter, some way you didn't, it's not just m, right? It's a lambda over m or something like that can also come.
I mean, it's a fantastic question, and I have to admit, I've never thought about it. Yeah. So in these statements, I've made no assumptions. This is a entirely non-perturbative statement. This is just using this follows directly from the Kallen-Lehman representation.
This part is fine. Yeah.
Yeah. However, yes, exactly. So imagine we had, the Higgs is coupled to some new chiral fermions with gauge charges and things like this, and they get all of their mass from the Higgs, but they're still BSM states. How do I see decoupling, the violation of decoupling occurring in this language? I don't know. I think it's a really important question, and I don't know the answer.
Maybe we can discuss it a bit more at the end then.
Okay.
Yeah. Maybe. I think I'm not trying to dismiss the question. I think it's a really important question, but I just don't know the answer. I'm afraid at the minute. I want to think about it.
Okay, yeah, let's move on.
Thank you. There's a lot of me distracted now because I want to think about it. So yeah, so going forward, up to that, it would be fantastic to see really how decoupling, the violation of decoupling, can imprint on these sorts of quantities. It'd maybe be even more useful when I talk about scattering amplitudes rather than 2-point functions in a second. Maybe that'll shed some light on it. But okay, so now imagine we measure these EFT terms. So what we're measuring is the p-squared dependence. So imagine we could measure the Higgs propagator really, really well in some basis. So we measure these p-squared dependent coefficients. We don't actually measure these C's. What we measure are the what I'm calling AN, which is the C's over the relative powers of relevant powers of m squared. That's what you can measure, because you're measuring the coefficients of the p-squared expansion, not the coefficients of the p-squared over m-squared expansion. So what you do is you measure these ANs, but still this convergence criterion or fact must be imprinted somehow in the theory. And indeed, what it tells you is that, for example, if C2 has to be less than C1, then A2, which is C2 over m squared, has to be, or m to the 4, has to be less than A1 times m squared. And what that means is that, in fact, if you measure these two quantities, you can put an upper limit on where the theory has to be UV completed. And this is not the same upper limit as we're accustomed to with perturbative unitarity, for instance. So imagine you have these two, in the plane of C1 and C2, you can't actually measure C1 and C2. All you can measure is A1 and A2, and m squared is some unknown quantity. So for each m squared, you've got a point in this plane. So you measure these two things, and you've got a trajectory as you vary m squared. But actually, at some point, you might hit the regime where perturbative unitarity is violated. That's when a1 squared is comparable to a function of 4 pi's times a2. However, before you even hit that perturbative unitarity limit, it turns out that you can actually violate convergence. So any C2 above C1 is forbidden. And that puts a strict upper bound on where the cutoff must be. And this is something that none of us, when we wrote this paper, had seen in the literature before. Now, we didn't find any super useful applications of this, but there are still some neat observations you can make. The first, the only one I will discuss really, is to think about E plus E minus to mu plus mu minus. Now, these old accelerators, E plus E minus colliders, actually measured these cross sections very, very precisely at energies below the weak scale. But nonetheless, they were measuring it precisely enough that the effects of Z exchange were very, very noticeable. You see in these plots, right? You've got the cross sections falling, and then it goes up again to hit the Z pole and down again. But at the tail, when the tail of the Z is turning on, you're starting to get sensitivity to the BSM, to the Z pole even before you've hit the actual Z pole itself. It's interesting, but taking so this means that this p-squared expansion for this propagator so this 2-point function was actually measured. Taking into account the measurements that they made, it turns out that if you had used, in those days, of course, the Z had already been discovered at Hadron Collider, so it wasn't like this could never have actually been a useful thing to do. But nonetheless, those measurements were so precise that using convergence alone, you could have proven that the new physics contributions had to enter at below 170 GeV. So the Z had to have mass below 170 GeV. And this is actually much, much stronger than any perturbative unitarity limits, which would have been around the TeV scale. So this is something that if you have a really, really high precision measurement in an effective field theory, such that you can measure subsequent terms in the p-squared expansion, then using it, you can place a different set of, I think, quite interesting limits on where the scale of the UV completion has to come in. Okay. So what does this, I've missed an S, what does all of this have to do with the EFT of the Higgs sector? Well, in the Higgs sector, it's not so simple, right? Because we can't just write down one operator and with our eyes closed, just fire ahead and talk about these things. In reality, if there is new physics in the Higgs sector, that new physics, if it is decoupled, if we're working within an EFT, and we're working with SMEFT and not HEFT, where you would have non-decoupling effects like Toon put up earlier. if we're working within SMEFT, then the new physics is likely to generate a whole load of operators, and there's the operator basis that we should use is not clear at all, because all the different bases will be equivalent. And so what this means is that we don't really know the nature of the new physics to a great extent, other than the set of Wilson coefficients that are the set of modifications of amplitudes that we can measure. However, we can still sort of organize this beast of dimension 6 operators a little bit better to think about what measurements might be useful for the Higgs. And I think the most useful way to do this for me is to put h bar back into the action. I'm a strong advocate that it's a bad idea to set h bar to 1. And that's because h bar has units of Planck's constant, and this is very useful for organizing effective field theories, for instance, and in other places for organizing any quantum corrections. We can see this already when you put h bar back into the action. You see that scalars have fields have units of essentially 1 over length times coupling. Coupling becomes dimension-full quantity. That's why the electromagnetic fine structure constant is h bar, scales like h bar e squared, because only the quantity h bar e squared is dimensionless. So that's the sort of the scale of the dimensionless quantum corrections. But it's very useful in EFTs as well. I'm sure you all know this, by the way, but I'm just repeating I'm just making sure it's I've discussed it for the following slides. Take, for instance, the Fermi interaction. We have some 4 fermion interaction and divided by some scale in the denominator, but that scale actually has to have dimensions of mass divided by coupling. You can see this just by dimensional analysis alone. And what that means is that that scale in the denominator is not the scale of new physics or of the electroweak physics. There's no, unless there's some extraordinary coincidence, there's no pole or branch cut at that position, which at that scale, which determines where the new physics comes in. There's always a coupling in the game, and of course we know this in the electroweak theory. It's just literally mw divided by g. But had it been uv completed by anything else, there would always been a coupling in the game, and if that coupling were small, then the actual mass scale of the UV completions could have been quite low. If that coupling were large, then that could have been quite high. And just by measuring the operator alone, just by measuring Fermi's constant alone, one cannot tell. So it's useful then to organize all of these operators by not just by mass, by dimension, engineering dimension, which I've done here. These are all dimension 6, but also in terms of their coupling dimension. And then this operator here, you can see, is very special. So these are all, if you have new physics in the Higgs sector, you will generate all of these operators. If it's just in the Higgs and electroweak sector and gauge sector, not if it interacts with fermions, but at leading order, if it just interacts with Higgs and if it just interacts with bosons, these are the operators you generate. And you'll recognize a lot.
Matthew, just
yep. Yes.
So your sound.
Yes.
Sound.
Is there a problem with my microphone?
I think the problem was at my end. Continue.
Okay, thanks. Okay, so we see that this one.
I also have the same problem. So I guess if you back up a little and talk about the previous transparency again, it will be good.
To here?
I think the next one.
Next one.
This one. Okay. So organizing these operators by engineering dimension, we've got all the dimension 6 ones. And these are all of the operators that will be generated if new physics is in the Higgs and gauge sector. So if it interacts with fermions, you will generate other operators as well. But if at leading order, the new physics is just in the Higgs and electroweak sector, these are the leading order dimension 6 operators you will generate. And I've ordered them in terms of coupling constant dimension along the top here. Of course, famously, here's the Higgs to the 6 operator, which has the highest coupling dimension of all of the dimension 6 operators. Which is why it has all these nice properties, like not renormalizing the other operators at one loop and things like this. And this is the lowest one here, the lowest coupling dimension one. And so it's very special. This is the operator that essentially parameterizes deviations in how the Higgs moves.
I have a question there about that last. I mean, it straddles these things. So what do OB, OW have? G to the 0?
OB and OW. They have order G to the 1. because you see you've got 3 bosons and 3 derivatives.
Yeah, and those are then G squared. Sorry.
On the right. Yeah, so I've put, for the mixed ones, I've put the coupling dimension explicitly in.
Yeah, right.
There's G strong.
Okay,
and things
thanks.
Like. Yeah. Thanks. Okay, so, and this operator here is the one that parameterizes deviations in how the Higgs moves. This is the one that modifies the Higgs propagator. And this is not some new language, by the way. This is something that we've used literally for decades in the electroweak sector. We all know the Peskin-Takeuchi parameters. There's the S parameter and the T parameter. Well, it turns out the W parameter and the Y parameter, which correspond literally to these operators here, and this would be the Z parameter, are the same sort of thing, 4 derivatives, two bosons, and they give the same corrections, analogous corrections to the propagators of the W and Z bosons, where the propagator takes the sort of this canonical form plus some constant piece, and you see relative to this is growing by a factor p squared compared to this one at high p squared. And this generates what looks like contact interactions. And indeed, if you change effective field theory basis to eliminate these operators, what you will generate is a bunch of contact operators between things like fermions and so on. So we've been here before, and one of the observations we made in our paper was that, you know, we should really, now as we approach the sort of the precision Higgs era, hopefully in the future, use the same sort of language and tools to think about the Higgs. And so it's natural to extend these precision electroweak parameters to the Higgs precision parameters. And then there's an analogous parameter to the W and Y parameter, which we call the H parameter, which is essentially the Wilson coefficient of this operator. And it gives the exact same sort of corrections to the Higgs propagator. Of course, this is basis dependent. You know, if you change basis, then you will get 4 fermion operators with this coefficient here. So I'm not claiming that this is somehow a unique basis, but nonetheless, just like the way we talk about the W and Y parameters, we should talk about this parameter, this H parameter. And it turns out that it's very, very hard to measure. The most promising place to probe it is really in 4-top production. You see, with the W's and Z's, it was nice because with W and Z, you can do Drell-Yan, especially the Hadron Collider at high p squared, where these effects will be big. You can do Drell-Yan type, you know, QQ bar to a pair of leptons, for instance, and you can pump all that p squared through the propagator and get really amazing constraints. But we can't do that. There's no Drell-Yan for the Higgs, because the light quarks are so weakly coupled to the Higgs. So somehow we have to put the Higgs off shell somewhere. And we played around with lots of different processes, and 4 tops seems to be the most promising for us. And so the best way to put the Higgs off shell at high p squared is in diagrams like this at a Hadron Collider. And just in terms of normalization, that coefficient, Wilson coefficient, C box over m squared, we're writing it as you do with the W and Y parameters as h hat over mh squared. And these are the sort of constraints you can get. What we did is we assume a sort of a scale for the cutoff, and so that we're not violating the effective field theory validity for each value of the cutoff, we actually discard any events where the total center of mass energy is above that cutoff. So this is very conservative, because what you really only need to exclude is events where there's more p squared than the cutoff going through here, and we're actually excluding all of them. So you can potentially do better, I think, if you're smart with kinematics, but we didn't go down that road. And so what sort of constraints can you get?
Maybe from one slide behind, and then, yeah, from here. Thanks.
Okie doke. So yes, so to probe the presence of these modifications, we have to take the Higgs off shell. And as I said before, you know, you can't do Drell-Yan with a Higgs, unlike the W and Y parameters at a proton collider, where you want to, where you can have QQ bar through an off-shell W or Z, pumping a huge amount of p squared through there to, for example, a pair of leptons. You can't do that with the Higgs. The Higgs is much more challenging. And we found that the most promising way to do this is with 4 tops. And we, for any given assumption about where the operator's UV completed, we discarded any events with a total center of mass energy above that cutoff. And these are the results we get in terms of sensitivity. Here is for different systematic uncertainty assumptions, our projection for high-Lumi LHC. And this is the projection for the sensitivity at 100 TeV. This is the H parameter on the left-hand side here. And this is as a function of the cutoff. And we've put our contours of extremely strongly coupled UV completion. So for a cutoff of 2 TeV, the H parameter would be, 0.8 or something like this for very strongly coupled. For pretty strongly coupled, violating, so this one here would really require some sort of, next leading order corrections to be as big as the leading order ones to sort of rescue you from unitarity. Here, if we just assume that the leading correction is saturating perturbative unitarity, then that is this. So this is a more sensible sort of strongly coupled theory. And then if we assume that just the Wilson coefficient in terms of the mass squared in the denominator is of order 1, then this is what you get here. So this is just sort of a moderately coupled UV completion. And we can see that at high Lumi, all you can actually sensibly probe in a self-consistent manner is strongly coupled theories. You don't really have access to very interesting classes of UV completions. And if it does much better as you go to 100 TeV, where you can start to probe much more realistic UV completions of this operator. Although I should say that CMS did an analysis, they sort of used their own four-top analysis, because there are many four-top analyses that are already out there that can just be essentially recast for this particular operator. They do a bit better. So they are already with 137 inverse points getting H hat to be less than about 0.12. So they're already around here. So that's pretty good. But nonetheless, this is very, very challenging. So the question of, how does the Higgs move? If we want to discuss that with some lay person in the street or in a pub or whatever, then the answer is that actually we're going to have to do an awful lot of work before we can actually constrain BSM modifications to the Higgs propagator, before we can claim that we've measured it to be standard model-like to any great accuracy. Of course, the pole is very standard model-like. There is a pole, but and the width is very standard model-like, but actually the p-squared dependence of the propagator we have no sensitive probes of yet, and we may not for some time. Okay, and just one little comment before I go on to a completely different set of things. This, we noted in our paper that this sort of logic applies in much more robust, because a robust scenario. So a two-point function is not really an observable. A two-point function is something that can be changed by field view definitions, things like this. So you can only state it within a given Lagrangian. You can calculate a two-point function, but it's not in its own right an observable. But to go beyond this, then you can look at things like forward scattering amplitudes, which are observables. And then, they're independent of any field view definitions or anything you can do. And a similar sort of logic applies. Essentially, it's just a close cousin of this. So if you have some forward scattering amplitude, a scalar forward scattering amplitude, which takes a form like this, then where by the optical theorem, this is the imaginary part of the forward scattering amplitude in here and in here. And then we can do exactly the same thing. If new physics contributions are above some scale m, and we do an expansion in s over m squared, then you can extract, just by Taylor expanding this, an analogous set of coefficients. We called them the bn's, and they satisfy exactly the same classes of convergence relations. And this is even more powerful, because it's telling you that if you had amplitudes, you can't have amplitudes that are arbitrarily soft. You can't have amplitudes where the momentum dependence only turns on at 20th order or something like this. The quantum field theory requires you would have 18th order and 16th order and things like this before that. So this is also a very useful thing and powerful thing. And it applies to any scalar forward scattering amplitude. And there's recent papers. There was a paper that came out shortly after ours, and this one here, which by Riccardo Bertazzi and Brando Ballazzini and collaborators, which consider similar, uses similar arguments, but much more detailed than what we did. And there are some other sort of relatively cute things you can do with this. So for example, if you take the forward limit of the Veneziano amplitude, which is this sort of string scattering amplitude, you get this function here. It's a very simple function. And when you Taylor expand it, the Taylor expansion in S actually gives you these so-called Bernoulli numbers. And this convergence relation, you can take it as n goes to infinity. You find in just from that general function that the ratio, the bn's have to approach, or the cn's have to approach 1. And then the fact that this ratio is approaching 1 tells you that you have this relationship for this quantity here. So I've flipped this around. It has to be equal to minus pi squared. And this is just sort of a cute result that was derived relatively recently, entirely independently in number theory. So there's sort of some interesting things perhaps to play around with there, although this is not a rigorous mathematical result. It was just a sort of a fun thing to note. Okay, so my last 15 minutes, I want to talk about something completely different, which is, well, not completely different, which is applying these sorts of dispersion relation ideas when you're not in an EFT. And I think this is probably, in my mind, as a sort of a BSMer, this is in my mind, probably the most interesting place to play with these dispersion relations, because it's completely uncovered, untouched, really, in my mind. You know, there's been a huge amount of effort trying to generalize the effects of heavy new physics using effective field theories, which has been studied very thoroughly. But actually, we can generalize when we're not in an effective field theory. We can generalize to some extent when states are light by using these sort of relatively robust quantum field theory results. And that was the idea. So the view of this part is to really think about dark sectors. You know, so we now know that the evidence for dark matter is overwhelming. I'm not going to list verbally list all of the pieces of evidence, but it's really irrefutable. Yet we have no idea what it is at the particle level. But furthermore, for me, I take this as a strong hint that there are dark sectors, or a dark sector at least, because if you look at the standard model, all of the energy budget of matter may be taken up cosmologically by essentially the proton. But that doesn't mean that life is just a proton, an electron, and a photon, right? In the standard model, there's all of these particles. It's not minimal by any stretch of the imagination. There's a lot going on in the standard model. There's a lot of particles. There's 3 different gauge groups and so on. All of these Yukawa couplings, where they come from. It's not minimal. It satisfies Occam's razor because it's the most minimal explanation we have for the behavior of matter. So it's minimal in that sense. It's minimal as an explanation, but it's not minimal structurally. I mean, look at it. There's a lot going on. Furthermore, the phenomena that occur in the standard model is by no means minimal either. You know, we see atoms and molecules, these giant nuclei that are bound together by gravity, which is neutron stars. So I strongly believe that the evidence for dark matter should be viewed by analogy with the standard model. If we didn't understand the standard model, we were looking, there's sort of 18% of matter was just something and we might assume it's just one particle, and we'd assume it's something like the proton, perhaps the proton and the electron, and it maybe in hydrogen or something, and that would completely miss the point of the visible sector. And we should be careful not to make the same mistake of the dark sector. And so it could be that the dark sector contains stable heavy states, but also it could be that it contains all sorts of other things as well. And it may be that it's the light mediators that open the window into the dark sector. Just, you know, we've explored the visible sector with light, with photons, and their masses. They don't make up the mass budget of or the energy budget of the visible sector cosmologically. Yet they're somehow the most important states for exploring the visible sector. So imagine we have some new states beyond the standard model, and they're light, they're not heavy. How can we make progress in trying to search for them? So of course we can search for their effects if they're very light in fifth force experiments, but fifth force experiments have not really been generalized to a large extent. The only model that's really used is a simple Yukawa force, what you get from tree level exchange of, say, a vector boson or a scalar. But we can do better than that because we can understand the general properties of these sorts of states, the influence of these sorts of states in a much more all-encompassing manner by using dispersion relations. So imagine we have some operator that contains hidden sector states. It could be a single state. It could be 3 or 4 states. It could be a state that interacts with its own strongly coupled sector, which is a big mess. It could be a quasi-conformal sector, who knows? So imagine you have some operator like this. Then fifth forces will be generated by diagrams like this, where you scatter essentially standard model states and you exchange this operator. So you have an operator insertion here, and you have an operator insertion here. If this were one state, one hidden sector scalar, for instance, you would just have a tree level diagram where you create the scalar here and kill it here, and in between you just have some scalar propagator. But operators have propagators too, and that's just the Kallen-Lehman representation. And so we can just insert the Kallen-Lehman representation into Born's approximation to derive the form of fifth forces that's completely general in the case where the fifth force is like this. So there's some weak coupling here and some weak coupling here. So you capture all of the force by this correlation function. Of course, if the couplings were big, you might have multiple, maybe four operator insertions or 7 or something like this, and then or 8, then you have to use a different approach. But if to a good approximation, you just have 2 operator insertions, so you have weak coupling to us, which seems reasonable, then it's captured in this way. So you can insert it into Born's approximation because the matrix element is related to the potential in this way. And we know what the propagator is because that's just the Kallen-Lehman propagator. And so we can derive the form of the force for a general scalar operator. So as I said, this operator could contain one field or many fields, or a few fields from a quasi-conformal sector or something like this. It doesn't matter. Always the form of the force you will generate if these operators are scalar operators is like this. And again, you see how you recover the Yukawa force in the simple case that it's a single scalar exchange, because rho just becomes a delta function, and then you get lambda squared over 2 pi r, and then you get e to the minus mr, because rho becomes mu squared minus delta of mu squared minus m squared. Furthermore, the positivity of the density of states here implies always an attractive force. So there's no scalar operators you can cook up that will give you a repulsive force, so long as they satisfy the postulates of quantum field theory. Furthermore, you can differentiate it and you see that there won't even be any turning points. You can't get a scalar force from scalar operators that gets weaker and stronger, or stronger and weaker. It will always get weaker. And you can see that just if you differentiate it with respect to r, you see that the sign of both terms is the same, and then positivity fixes the sign of the integral. So you'd never get a turning point. Of course, if you interfere operators of different spin, because different spin operators can give you different forces, and you interfere them, then you could have turning points. You could have forces that are approximately attractive in one regime and approximately and repulsive in another regime. Not approximately. But if you just have scalar operators, then they will always be attractive. And we can actually use this set of tools to quite easily for specific models can extract some results for.
I missed your qualification in the previous thing. So I understand the positivity of rho gives you attractive potentials. Did you say that? Did you qualify it in some way? Did you say that if you go beyond scalar, then something else happens?
So if you go, so like these statements only apply for scalar if the operators are scalar. So if the hidden sector has operators that are vector operators, or fermionic operators, things like this.
Right. I mean the density of states is still positive, right?
Yes, but so for example, if you do vector exchange, you get the similar sort of thing, but with the opposite sign. Because
I see. So in this language, your potential would be a tensor potential or something.
Well, yeah, you can even calculate VR just like in electromagnetism. That's a vector exchange, but VR is like this, but it's and obviously the mass of the photon is 0, but you get the opposite sign between two states that are identical, so between 2 electrons.
So where does that come from? The density of states is still positive, but it comes from the Dirac structure in the standard model.
No, it's not even. You can do Kallen-Lehman, this guy here, for vector. Say you carried vector indices here and here. This would be mu and this would be nu. Then your propagator looks like this, and there's a piece here that goes like g nu, and then there's a different density of states. Now for a vector, you get 2 densities of states, a different density of states for something that goes like p mu. and then we contract them in. So it's not you're not assuming that it's actually just a vector state like a Z or something. This is just a vector operator. So this could be, psi, gamma, mu, psi. That's O. It's a vector operator, and these are and what I've been talking about are scalar operators. So it's very, very general, and this is where Weinberg's sum rules came for.
So it doesn't become a potential like this. There's the standard model part has some tensor structure, and whatever you're calling the potential will have a tensor structure too.
No, there wouldn't be a tensor structure. So for example, you can calculate the potential between two electrons, and what you have there is photon exchange. So that's a vector operator, and you don't have a G mu nu. You just have the normal Coulomb potential, but it just has the opposite sign to this. And so
okay, I'm missing something here. So if we go back to your Källén-Lehmann representation,
yes.
The difference is that you'll have a polarization tensor on top of this 1 by q squared piece.
Exactly, in the propagator. But the matrix element is the thing for the potential. See this bit here, and the matrix element is still a scalar.
I see. Okay. Thanks. Yeah.
No worries. Thanks for the question. Okay, doke. So we can also use this to calculate some specific results for example models. So for example, imagine you had the standard model operator. Maybe this is like a pair of neutrons or something like this, is coupled to a pair of light scalars or a pair of light fermions or light vectors, or even to two derivatively coupled scalars.
So let me try to just understand this. I'm sorry, I'm taking it.
This is good. Yes.
So if we didn't know that gravity existed, okay, so then we could look at gravity, and the coupling to gravity is it's not through a scalar operator, right? So
no, but the matrix element, so the potential depends on the matrix element. So the matrix element between two planets is still a scalar quantity.
Yeah. Okay. Fine. Thanks. Yeah.
No worries. So imagine you want to know what the fifth force generated by these guys is. So normally you would do, and by the way, we aren't the first to think about these models. There are papers by Sylvain Fichet and collaborators that have studied these before. But what we did, which is slightly different, is that as you would naively do, those guys calculated these matrix elements, doing loop integrals and things like this. But actually, for our purposes, we can just use the optical theorem, because we know that the potential takes this form here. But rho in the Kallen-Lehmann representation is just, because of the optical theorem, is just the imaginary part of the propagator. So what we need to do is cut these diagrams to find the imaginary part, and then we're done. Then we do, because it's the optical theorem, we don't do a loop integral, but we do a density of states integral, essentially, using the optical theorem. And you can immediately extract the form of rho for all of these different models. And these are the different forms. There's always a heaviside theta function where rho is 0 below the mass scale of those particles. And then you can do the integral over mu squared to derive the scalar potential, and it takes these forms here, which for most part, up to I think potential typos, matches the results in these paper here. You can also use this to go even beyond that. I don't advocate this, because in my mind, the whole power of this approach isn't to do perturbative things. It's to think about strongly coupled hidden sectors and conformal hidden sectors, things like this. So I'm highlighting these things just to demonstrate that it's a useful way of thinking about it, but perturbative models aren't necessarily the way anyone would want to run with this. But nonetheless, you can keep doing this at higher loops. So imagine you had the standard model, like a neutron, for instance, is coupled to 3 scalars. Then you get 2 loop exchange, and again you can calculate the potential, calculate rho and the potential through the optical theorem just by cutting this diagram in half. And then you get a 3-body phase space integral rather than a loop integral. And you get that rho is this guy. These are some elliptical functions. You can also integrate over that guy to get the scalar potential. But I think maybe what's the most interesting thing is that this way of capturing general scalar forces is really very, very general. And you can write the experimental observables themselves that are used in fifth force experiments to set limits directly in terms of rho. So this is the most general and compact way you can parameterize these things. So rather than assuming some model for fifth force, then deriving all of the potential stuff, and then calculating each experimental observable that you might be interested in for that model. You can do it the other way around. You can calculate all of the experimental observables as a function of the general density of states. And then once you have your model, you just plug that density of states in here and you're done. So you can do it from molecular spectroscopy, bouncing neutrons, experiments where you have effective planar geometry, so like experiments where you have a sort of a sphere near a plane and you look at the force between both of them. Cold neutron scattering, lunar perihelion precession, which is sort of for very long range fifth forces, so very low energy. And applying it in these ways, I can show you the limits, which match that other paper very well for the most part. And so this is for a standard Yukawa interaction, which has really sort of been the playground of fifth force experiments, I think, for a long time. This is going beyond to like one loop exchange of scalars here and so on. But then as you go to higher and higher dimension operators, so this is interaction D, which is this guy here with the derivatives, or this interaction where you have a two loop exchange, so you have three scalars. What we see is that these experiments here, the molecular spectroscopy, because they're the shortest range ones, are the most sensitive because these are higher dimension operators, so they are become more and more relevant, more and more, important as you go to smaller scales, to higher energies, they grow faster. So for these sorts of models, that's the way it scales. As I said, though, in my opinion, the really interesting thing to think about is probably what happens when the hidden sector is strongly coupled and conformal and all sorts of things where you can't even do these perturbative calculations in the first place. What would a hidden sector violation of QFT fundamentals look like? Well, as I said, you could have forces that change sign if you had interference between different types of forces, vector forces and scalar forces, for instance. But if you find that these forces really are scalar, coming through scalar operators, and you find that they turn over, they change, from being attractive to repulsive and things like this, then what you would observe in experiments would be, your limits under those sorts of assumptions would look like this. So the phenomenology would be very different, and the interplay between which experiments are most important would actually change. Now, this is entirely wildly speculative, and I'm just giving this plot as an example. What we did is we took a density of states that was positive for a while and then negative for a while for a little bit longer. So then you get this forces that at short distances are attractive and long distances become repulsive. And we put, obviously, the region with a negative density of states is inconsistent with QFT. But this is just to sort of hint that, we know that probably these fundamentals break down, especially things like locality, at very short distances, because something's going to have to take over and explain quantum gravity. But I think it's interesting. It's not really considered much, but I think it's also interesting to speculate that maybe there's some really weird stuff going on in nature, and we haven't, at energies that we can access, but we haven't observed it yet. Because that stuff is very, very weakly coupled to me. This is sort of a fun thought experiment, I think, although I'm not proposing it as something we should necessarily put a lot of effort into searching for experimentally. Okay, so I should summarize, and I've run 5 minutes over. So, I'm quite intrigued by these early days of QFT, where some pioneers found very beautiful and I think powerful general results that are entirely non-perturbative. These results are often like little islands. They don't necessarily form a part of a cohesive whole. They're often little islands. I see the Kallen-Lehman representation as sort of being the progenitor of a lot of these things, and it's sort of, to me, is an island of a result rather than being part of some cohesive, comprehensive whole. Nonetheless, we can still use it in particle physics, and we can use it when we're thinking about quantum field theories and beyond the standard model physics. So I think this work was quite pioneering. Sadly, you may know that Kallen died when he was flying his plane to CERN, I think from Sweden or something like this. So it's very sad that we didn't get to see more beautiful results from him. He was very young when that occurred. So I think these dispersion relations are very powerful tools, and they give us lots of interesting things. So we get not only the sort of positivity constraints that we normally think about in quantum field theories, in effective field theory, ever since the sort of very pioneering, I guess, papers by like Nima Kani-Hamed, Ricardo Rotazzi, I think Alberto Nicholas, and Alan Adams and co. But we also, with this approach, we also get results that go beyond positivity, that basically relate successive terms in the p-squared expansion. We call this convergence, which I think is very intriguing. Of course, it has less experimental relevance because to test convergence, you have to measure subsequent powers in the p-squared expansion. That is difficult in an effective field theory, but if you could, then this is relevant. But it's maybe more interesting just from a structural sense to see that this information is encoded already in quantum field theories. And when new states are not decoupled and we're not in an effective field theory setup, we really don't have many theoretical tools at our disposal. And I think these dispersion relations really do give us another set of interesting tools that we can use to try and generalize when new physics is light. And that's very difficult. Normally what we do for light new physics is we have to write down a model and we calculate. What I'm proposing is that actually maybe there's another way of looking at this that sort of could have more limited impact, but could have a similar sort of role to play in BSM physics that effective field theories have had. And last of all, I was trying to think about analogies about this situation where we write down models for light new physics, and then we try to, test their experimental search for them experimentally, see what the experimental limits are, and then write down a different model and do the same. And somehow this sort of reminds me a little bit of Maxwell's process, where he wrote down these theories with rotating vertices and vortices and all these sorts of things. And these models, these toy models, really guided the development of how we understand classical electromagnetism. So they were very, very useful, but of course they were missing the point, and the point only emerged afterwards of this general structure. And I sort of think that maybe as we seek to look beyond the standard model, especially at low energies when the weakly coupled frontier, but also at highest energies, we should maybe not let our toy models speak too loudly, and search a little bit deeper into quantum field theory to see if we can generalize what is going on there, or learn some lessons that may have been missed because of focusing too much on specific models. And I should really wrap up. I'm way over. Thanks.
Okay, thank you. So if there are any questions, please go ahead. So Tuhin, unfortunately, was not able to join back because of the technical issues. So I think he'll get back to you a bit later.
Okay.
I was wondering so if there. Okay, Surendu has a question, but we can't hear you.
No, I don't have a question. Sorry.
Okay. So I had just one quick question. So there was a period, when there was some speculation that the hidden sector could be conformal. And in that case, the O expectation value that you wrote down, or the spectral density, if you want, must have a simpler structure, or will have more symmetries. Has somebody analyzed, or have you thought about what happens in those cases?
Oh, I haven't done it yet. So,
Okay.
well, I believe that rho in those cases will probably be approximately flat.
Okay.
For some energy range, because essentially the density of states, if the theory is conformal, I imagine the density of states isn't changing rapidly. But I didn't study it. People have looked at fifth forces from conformal hidden sectors before. There's one paper by Philip Tonedo and co. But what they did, they didn't use this sort of general formalism. So what they did is they wrote down a model where they were coupled to a conformal sector, and then I think they used holography. So they used some dual 5D theory to work out, to calculate what the form of the fifth force would be. But that was for a particular model. And so generalizing using this Källén-Lehmann representation, I think would be interesting, but I haven't done it. And I think to some extent, in our paper, that's maybe what we should have done rather than these perturbative models, because these perturbative models are good for validating the approach, but really the whole point of using a non-perturbative tool is to apply it to scenarios where you can't use perturbation theory. So I think that would be a very interesting thing to do.
So I guess if there are no further questions, then just thank the speaker, and I'll stop the recording, and see you next week then.
Thank you very much. Bye-bye.
Thank you.